right, this is the beginnings of classwork 29. This is something that I normally go through and do part of and then leave it for you to complete the rest of it on your own. So we are introducing a new topic today. We're going to investigate one of the big questions that initially led to the development of calculus, which is how do you find the area of an object that's got curved sides? Not necessarily a circle or something like that that we have a nice formula for, but something a bit more irregular. Or in general, what if I talk about finding the area under a curve? We use a technique here called Riemann sums, developed by a German mathematician, Riemann, many years ago. And we're actually going to start by investigating the area of a shape that we actually already know, a piece of a circle, just to kind of see how this technique works. And then we'll go on to use the same technique in other situations where we don't know the answer ahead of time. So I would like to start by saying, just using a standard geometry formula, I want the area of a quarter of a circle of radius 4. Well, I know in general the area of a circle is pi r squared. And since I only want a fourth of that, I will multiply by 1/4 to get the area of the quarter circle. And if I plug in 4 for my radius, I've got about 12.566 as the area of my quarter circle. Okay. So we're going to go with that as our known value of the area we're going to try to find. And then we're going to go ahead and we're going to then say, hey, what if I didn't have that nice formula? Is there another way that I could arrive at approximately the same answer? All right. So first of all, I'd like to represent my area, my quarter circle, as a function. In order to do that, I'm going to start with the equation of just a whole circle, centered at the origin with radius 4. And that, I'm sure you've seen this kind of thing before, like in pre-calc or something. Equation of a circle is x squared plus y squared equals the radius squared, 16 in this case. If I solve that equation for y squared would be 16 minus x squared, and y would be plus or minus the square root of 16 minus x squared. That plus or minus on the y values, if you think about your circle, if you were to graph it, that plus or minus on the y values is saying positive y's, which would be the top half of the circle, and the negative y's, which would be the bottom half of that circle. So if I choose just the positive square root, I'm going to have just the top half, going from -4 to 4. Whoops, sorry about that. All right, I only wanted a quarter of a circle, not a half of a circle. And so I'm going to further restrict the domain to just from 0 to 4. That way I'll just get that quarter circle like I want it. So this is what I'm going to be doing. I'm going to be using this as my function. Y is the square root of 16 minus x squared on this interval from 0 to 4. And the question that I'm going to ask myself is, how could I find the area under that curve but above the x-axis? In other words, how could I actually find the area of this quarter circle if I didn't already have a nice geometry formula like pi r squared? Because in general, when our function doesn't make a recognizable geometric shape like that, we won't have a nice formula to use. What we're going to be doing is we're going to be subdividing the area that we want to find into pieces that are rectangular. Now, of course, perfect rectangles won't exactly fit underneath that graph, but I can at least use them to approximate the area. So let's just start by defining our circle here, or quarter circle, I guess I should say. I went from 0 to 4. And there was that graph. It actually comes down here, which is y, or f of x, equals the square root of 16 minus x squared. All right, to approximate the area, I'm going to use 4 rectangles. And for right now, as it says here, drawing my 4 rectangles, I'm going to use the left endpoint on my curve here to determine the heights. Try and get this so you can see the whole thing. There we go. So my first rectangle, well, actually, first of all, I should probably point out that if I'm going to draw 4 rectangles, each one would have a base of 1 unit. And so if I start on my very leftmost endpoint, that would be up here with a y value of 4. And I'm just going to kind of make a rectangle by leveling it off. And I'm going to say the area of this whole rectangle can be used to approximate the area under the circle between 0 and 1. Right? Now, clearly it's not perfect. There's actually a little bit of extra area up here in the corner that belongs to the rectangle that wasn't really in the circle. But this is an approximation, so I'm going to be okay with that. So you'll see down at the bottom of the page in my little chart, my first rectangle has a base of 1, and the height we saw was 4. So the area of that rectangle, length times width, is just 4. I'm going to do that 3 more times, once in each of those intervals, and get 3 more rectangles. So for my next rectangle, it starts here at x equal 1. So I'm going to go up and say the left endpoint would be about here. I'm going to level it off. And I'm going to draw that rectangle. Once again, I notice that even more so this time, there's some extra area inside of the rectangle up in that right-hand corner that doesn't really belong to the circle. But again, I'm going to be okay with that because right now I'm just approximating. In the chart, I'm going to move the paper in a minute, but in the chart at the bottom, you can see the base again is 1. And it says that the height is the square root of 15. So while I still have this visible, I want to talk about why we could say that that height was the square root of 15. The height is really this y value. And notice that it happens when x is 1. So if I just take my function and I plug in x equals 1, I'm going to get square root of 15 there. And that determines the height of the whole rectangle. So down here in rectangle number 2, again the base was 1. We now saw y, the height was the square root of 15. So area is length times width, and I approximated that to 3 decimal places, 3.873. All right, we're going to do 2 more. I'm over here to x equal 2 now. And so that is going to determine the height of my rectangle. Level it off. And you might be knowing that kind of the excess here up in this corner gets a little worse every time. My approximating rectangle is actually best at the beginning. I get a little bit more excess area every single time here. All right, I'm going to want the area of that blue rectangle, and to get that, I need that y value, which occurred when x was 2. So plugging 2 into my function, I would have the square root of 16 minus 4, or the square root of 12. So my third rectangle still has a base of 1. We just calculated the height was the square root of 12. So area, 1 times the square root of 12, is about 3.464. All right, last one. I'm over here to x equals 3. So that's the height on my fourth rectangle. Whole bunch of extra this time. But I'm going to follow my technique, and I'm going to still use this rectangle to approximate the area under the circle. And let's see here. This time, my base is still 1. And the height, this y value, is when x equals 3. So square root of 16 minus 9 would be the square root of 7 for that height. And so my area, 1 times the square root of 7, is about 2.646. All right, so if I now want to say about what is the area of that quarter circle, what I'm going to do is add up the areas of the 4 rectangles and say they make an approximation for the area of the quarter circle. Now I can visually see really easily I'm probably going to be way high here. It's going to be way too big. But as a starting point is all I'm after right now. So let's do that. If I add up all 4 areas, I have 13.983. Now, as a reminder, that is definitely not a very good approximation, right? The actual quarter circle we knew had an area of 12.566. So, as expected, that's a huge overestimate. But it's the concept, it's the idea that I want to get at here. And then the next question I'm kind of going to ask us is, all right, if this is an idea of a way to estimate area, how could we get a better area estimate? Well, you may have noticed that there wasn't as much extra early on, and it got worse and worse. So the trick that I'm going to use is actually to cut this into smaller and smaller rectangles, so I have more rectangles. And that way, I'll have more rectangles with less error in them. Okay. So I'm just going to get us started on this next one. You're going to be left to finish this next one by yourself. But if we repeat this whole process, and this time we use 8 rectangles to approximate the area, we're going to experiment with that, but we're kind of expecting that it's going to give us something closer to the actual area of the quarter circle. So let's set this up. Again, I'm just going to kind of outline the quarter circle whose area I'm trying to find. And this time, if I want 8 rectangles, notice that I have a total distance, a total interval here on the x-axis with length 4. So if I'm going to fit 8 rectangles into that, rather, each one is going to have to be split up into a base of 1/2. Okay. I want to mention that the base of the rectangles, which we usually call delta x, it's a little piece of the x-axis, there's a nice formula for that. If you take the length of your interval, which you can always get by just taking the right end point minus the left, we usually say that's b minus a, and divide by n, the number of rectangles, that's going to give you the length of each base. In this case, I know that was really easy to figure out that it would be 1/2, but this gives you a general method of doing that, even in cases where maybe it's not quite so obvious. So in this case, my interval goes from 0 to 4. That's the a and the b in this little formula. And the number of rectangles is n, and we wanted 8. So if I actually follow that formula and take 4 minus 0 divided by 8, notice 4/8 is the 1/2. Exactly what we expected. But again, it gives me a formula that I can make use of in other cases where it's not quite so obvious. All right, so if the base is going to be 1/2, I'm going to mark that off here. This would be 1/2 or 0.5, 1, 1.5, 2, 2.5, 3, and 3.5. I will still start with my first rectangle over here on the left. I know the height's 4. And when I level it off this time, I'm only going halfway, because I want to make sure my first rectangle only has a base of 1/2. Area of that first rectangle is fairly easy. The base is 1/2. The height is clearly 4. And so you can see down here I did length times width, or base times height, 0.5 times 4 to get the 2 for the area of that first rectangle. We'll talk about the second one, and then I'm going to leave you to complete the rest of them on your own. So in my second rectangle, it starts here at x equals 0.5, about here. I'm leveling that one off. And there's my second approximating rectangle. And you'll notice that these do both have just a little tiny bit of extra area compared to the circle, but not much, right? As a matter of fact, if you compare the little tiny bits of extra area there to the bit of extra area on the first rectangle from 0 to 1 here, you'll notice that that's actually more than the 2 pieces I have here. So I am creating less error in this process. All right, I know my base always is going to be 1/2 in this problem, but I do need to get a height. So let's see, that would be this y value right here when x is 1/2. And I'm still using the same circle, so square root of 16 minus 0.5 squared. 16 minus 0.25 would be 15.75. And down here, there's the base, 0.5, the height, square root of 15.75, multiplied those together to get area. So part of your assignment on this classwork assignment is going to be to complete this problem, do the other 6 rectangles down here, and then add them up to get your area approximation. What I'm hoping you're going to see is that this one was too big by a lot compared to the actual known area, right? The one that you're going to get with the 8 rectangles is still going to be too big, but hopefully you'll find that it's closer to the real area than our 13.983 was. All right. So that's going to bring us to the next page. You're going to answer these 3 questions at the top of the page on your own. I've already pretty much given you a clue as to how to do that. And we're going to then talk a little bit here about number 4. These estimates that we've been making are called upper Riemann sums. Again, mathematician Bernhard Riemann is the source of the name there. And the reason that they're called specifically upper sums is they're based on using rectangles that are larger than the actual curve. Formal name for that is circumscribed rectangles. And as we've talked about, and by the time you get here, you'll totally have realized, the more rectangles we use, the closer we actually get to the true area under the curve. Of course, the problem is the more rectangles we use, the longer and more annoying the problem gets. I'm having you do 8 rectangles, but if you started getting 50 or 100 or 1,000, naturally that would be a not very fun problem to sit and spend your entire day crunching numbers on. Fortunately, calculators and computers tend to be really good at those kinds of repetitive tasks where you're crunching numbers. And if you're good, you can probably even program your own calculator to do this. But if you don't want to take the time to do that, there is a nice little website here, this MathWorld website. And I'm going to recommend that you use that to go ahead and crunch these numbers for you. All right? So I'm going to go ahead and all the instructions are right there, but I'm going to go ahead and just kind of do this one with you. I'm going to go to that website momentarily, and you'll notice that we are going to repeat our area for 4 rectangles and 8 rectangles. At this stage of the game, we know the answer for 4, and you will know the answer for 8. And then we're going to totally rely on the technology after that to say, what if I used more and more and more rectangles? Okay. So I'm going to go get that website up. When you get there, it's going to look like this. And you'll notice that the first thing that I have to do is tell it what my function is. So I'm going to get the equation of our quarter circle in here. I don't know the square root notation for this, so I'm just going to use a 1/2 power. So I'll have 16 minus x squared raised to the 1/2 power. Make sure you've got those parentheses in there the same way I did, or it won't understand correctly. Our interval was from 0 to 4. And just to verify everything's working correctly, I'm going to go ahead and do the 4 rectangles, even though we've already done this by hand. Remember, we were using the left endpoints to determine the heights of our rectangles. Okay. I'm going to say replot down here. Oops, hang on just a sec here. All right, well, I had to abandon my website that I've been using for years because I could not make it work. So perhaps finally that website's become defunct or something. Anyway, there's a bunch of them out there. This is, I just really quick Googled and found this one. You can Google and find probably any number of them. But here's one if you're interested, this geogebra.org one. You can see the web link right up there, /m/h4p4cjs, capital T. So take a look at that or copy that link, and we'll just go ahead and use this GeoGebra website instead of the one that's in your assignment. My apologies there. So once I get there, whoops, I don't want it quite that big. Once I get there, I have my calculator down here. And again, I'm just going to put in my function. 16 minus x squared to the 1/2 power. Again, watch the parentheses. There's the quarter circle because the scale is not the same on the x and y axes. It looks a little elliptical, but it's actually a circle. And we are going from 0 to 4. And our first n value, we wanted 4 rectangles. I do want the left Riemann sum here, so I'm going to check that box. And you can see it drew the same 4 rectangles that we drew, and that 13.983 is exactly what we came up with. I can now change the n value and say, hey, let's use more rectangles. 8 was the next one. And I am having to uncheck and recheck the left box each time. But again, notice you can see that there's the 8 rectangles. There's a little bit less error this time. Gave us about 13.359. Right? I'm going to go ahead and I'm going to show you just visually the others that I asked for in the assignment. I asked you to use 25 rectangles. And again, I'm still using left endpoints at this stage. Notice with lots more rectangles now, the amount of little extra area hanging over the edge is getting much smaller. And 12.848 is much closer to the 12.566 that we know the actual area is. We're supposed to do 50 and 100 as well. There's 50. Again, you can see that this is now a pretty darn good close fit, right? Not a ton of leftover area. We're now at 12.713. And if I finally go to 100, we're at 12.642. So we're getting quite close to that 12.566. If I were to draw more rectangles, I could get closer yet. And in fact, you might start thinking about how many rectangles would I have to draw to get really, really close to the actual value of the area of that quarter circle. So anyway, when I don't actually ask you to draw and do by hand, you are welcome to use this GeoGebra website, or if you can get the Math World one working, feel free. But again, there's the link for the GeoGebra site that I did find that does work. All right, so that's how you're going to fill in the bottom here. All right. On the next page of the assignment, it asks you to repeat the whole process using this time inscribed rectangles, or in other words, rectangles that are going to be under the curve. And the way we're going to do that is by using the right endpoints to determine the heights instead of the left endpoints. So again, I'm just going to get you started on this. Here's our familiar little quarter circle again. And for this first time, let's see here. I think I said 4 rectangles. So n is 4. So we're just going with the 1, 2, 3, and 4, like we did the first time. And I'm going to run through this one. Something kind of interesting happens with the last rectangle, and I want to make sure you see it at least once here. So my first rectangle, this time over here at x equal 1, I'm going to use the right side of the rectangle to determine the height. And you'll notice that this time my rectangle remains underneath the actual graph of the circle. Right? So instead of having extra area, I'm actually missing some of the area that I should actually have. The y value that determined the height there was the one for x equals 1. So the square root of 16 minus 1 squared, or the square root of 15, is now the height of that first rectangle. So base of 1, height square root 15, and that gives me an area of about 3.873. Let's do 3 more. I'm going to go to my next rectangle, which would go from 1 to 2 on my base. And since I'm using the right endpoints, I'm using the height over here at 2 to level off my rectangle. And here's my area. Again, you'll notice that the area of the rectangle itself is actually a little bit smaller than the true area under my circle. The height function, I would have to plug in an x of 2 to figure out the height of that rectangle. So that's going to be the square root of 12. Base of 1, height is the square root of 12. About 3.464. All right, my next one goes from 2 to 3, and again, I want to use that right endpoint this time. Level off my rectangle. And I'm now missing quite a bit of area that should have been under the circle, but as we saw before, that happens. We know already that when we start using more rectangles, it'll get better. So my height function, y is the square root of 16 minus 3 squared, or the square root of 7. Uh, 2.646. And finally, this is actually the reason I was doing this much of this one. Look at what happens when you get to the fourth rectangle. Fourth rectangle would go from 3 to 4. And using right-hand endpoints, 4 is determining the height of the rectangle. But the actual value of the function there is 0. So in actual fact, my fourth rectangle is literally just a flat line with no area at all. The height here, y is 0. So base is 1, height is 0, giving me no area from that fourth rectangle. All right, just like we did before, we would add up the heights of all 4 rectangles. I know technically there's really only 3, but we saw what happened with that fourth one. And I have 9.983. As expected, this is a rather large underestimate of the actual area. We missed a lot of area that should have been under that circle. Okay. So, similar, and I'm going to start leaving out more stuff here for you to do, similar to what we did last time. On the next page, I'll be asking you to repeat this process using the inscribed rectangles, but do 8 rectangles this time. So draw the rectangles, fill out the chart down below, and come up with the area estimate for using 8 rectangles. You will answer a few questions at the top of the next page, and then you'll go back to whatever computer application you were able to get working, and you'll do more and more and more rectangles, hopefully seeing the area estimates get closer and closer to the value of the actual area of the quarter circle. I did want to make a mention of this last question down here. So look back at the 2 best estimates you have. That would be the n equal 100 estimates for both the upper and lower sums. And compare these to the actual area of the quarter circle. Okay. What I really want you to notice here is our actual area, remember way back in the beginning, was 12.566. if I just quickly bring that website up again, for the n equal 100, my left Riemann sum that had a little bit of extra area gave me 12.642. And my right sum, which I can get by clicking this other box down here, I'll get rid of the left one. There we go. Notice how this is slightly underneath the curve. The estimate there is 12.482. I'm keeping 3 decimal places. So my actual known area here, the 12.566, is definitely between those two values. If I didn't know this actual area, if I was working with a function whose area I couldn't have calculated using some nice geometry formula, I would now kind of have the actual area trapped between a lower estimate and an upper estimate. And that's actually going to be important when you do the next problem, and in fact the last problem on this assignment. All right, so in section 2, I am now going to ask us to go ahead and use the same process to find an area that we would not have been able to find using just traditional geometry. We're going to be approximating the area under the curve y equals x squared plus 1 on the interval from 0 to 2. So let's just think about what that looks like for a moment. Right. X squared plus 1 is just a parabola that's been shifted up 1. So it basically looks like that. And we wanted to go from 0 to 2. So your goal is going to be trying to figure out the area underneath this parabola, but still above the x-axis. So you're looking for the area inside there. Now, similar to what we were doing before, I'm asking you to do the 4 rectangle case by hand. So you're going to actually do the n equal 4 case by hand. You're going to take your picture, you're going to draw your rectangles, and then you're going to make your little chart, add up all your areas, and you're going to figure out that total area by hand, and I'll need to see the work down here to do that. Okay. That, however, is the only one I'm going to ask you to do by hand. Once you've gotten the n equal 4 done, you're then welcome to go back to the computer program and just get the rest of them off of that. Okay. This one, I'm asking you to do lower sums, so pick rectangles that are below the curve. And then on the next page, I'll be asking you to do the same thing using upper sums. Again, just the n equals 4 by hand. The rest of them you can use that computer app to figure out. On this last page, question number 3, kind of like the one that I just talked to you about, right? When we use the computer app to get lots and lots of rectangles done, we were able to basically trap our actual area between a lower and an upper estimate. That's the kind of thing I'm looking at here, is to make some conclusion. You'll now know the actual area that we're working with has got to be between 2 values that you have figured out. Right? This last question, actually you think, whew, I finally got to the end of this assignment, but hate to say it, I'm sorry. This is actually the one that you're going to need to do a bit more background work. You're going to need to watch the lecture videos for 4A. Before you can do that, it will give you the exact technique. Essentially what that's going to do is say, well, if 50 rectangles good, 100 rectangles is better, 1,000 rectangles would be even better, what's the best number of rectangles? The best number of rectangles would be an infinite number of rectangles. And to get an infinite number of rectangles, we're going to have to actually find a limit. So the video 4a will go through that whole process of how you find that limit, how you evaluate it, and after you've watched those, you'll be able to come and do that last problem.